Hello and welcome again to my Physics Online Video Lecture Supplement series. Today's short video, I want to talk a little bit about vector as opposed to scalar quantities, and specifically I'm going to do this in the context of kinematics because this is sort of one of the lectures that goes with my 1D and later kinematics set of lectures, if you will. So let's look a little bit at vector versus scalar quantities and how they might apply to kinematics and beyond. All right, so very basic definition or working definition. Vectors and scalars are two types of quantity. A scalar is a quantity that has magnitude only. So quantity only has magnitude. So that means that it has associated with it as a quantity, it is basically a number with units, or maybe without units, depending on whether it has units normally. All right, this is distinct from a vector, which is a quantity that has a magnitude, just as a scalar does, but it also contains information about direction. So a vector is a quantity which has both magnitude and direction. And how we can sort of state that magnitude and direction may vary depending upon how many dimensions we want to include and depending upon how we want to specify, like what kind of coordinate system we want to use. Okay, so let's give a simple example of each of these two things. Let's say that I am standing out in a field and I have another friend who's standing out in the field with me, and I look over towards where my friend is standing and I say, or I can see that the distance that I'd have to walk if I was going to get to my friend, straight line distance, would be let's say 15 meters. All right, so my friend is 15 meters away. Well, that's an example of a scalar quantity. It's just simply a magnitude. Now, I did state that this was via a straight line that I'd have to walk to get to him, and so I've included a little more information, strictly speaking, than the scalar itself has. But the distance between us is 15 meters. Now, it may also be that I'm in a field that's really more like in a marsh somewhere or a bog or something, and so there's paths or maybe like a little bridge that I can walk across and ways that I can get from where I am to my friend that is not a straight line. But assuming that I don't double back or anything like that, and I try to take the shortest path that I can to get to him, and I count how many steps I have taken to walk from where I am to where my friend is, what I've measured is a sort of distance. It's the distance that I will have traveled, and that is a scalar. Now, suppose that instead this field is maybe represented by this little green map right here. And suppose that I am standing, let's say like right here. So me, I'm here. My friend maybe is here. Okay. So if I wanted to walk a straight line between myself and my friend, or a more or less straight line from myself to my friend, I would have to take those 15 meters and go not only in a particular distance, not only the 15 meters, so here's my 15 meters, but I'd have to go in a particular direction to get there. If the only information I have is just walk 15 meters and you'll be to your friend, well, I could walk 15 meters from here to here and make it to my friend. I could also choose to walk 15 meters this way, let's say. This is also 15 meters. But as you can see, I won't really be where my friend is. And for some really two choices of 15 meters, I can actually end up the same 15 meters away from my friend that I started from. Okay, so in other words, I could have chosen to walk 15 meters this way, and where I ends up also being 15 meters. So this is 15 meters, this is 15 meters. Okay, so you can see that the direction that I walk to get from where I am to my friend matters. Now you may say this is a kind of a contrived example, in as much as if you were just told you're in a field and you're told the friend is 15 meters away, walk to your friend. You just kind of look for where your friend is, or maybe if you happen to be blind or seeing impaired, or your friend is obscured or whatever, you could have your friend call out to you and you could walk to him directly that way. But imagine now, instead of a friend, imagine that you have it's like you're on a treasure hunt, let's say, and you have a clue, and you're standing at that location, and the clue tells you that the next clue is 15 meters away. All right? So assuming that the clue is correct, assuming that it is exactly 15 meters, plus or minus maybe a few centimeters, from where you are standing to where the next clue is located, how might you find it? Well, basically, you're here, and what you might do is get a string that is 15 meters long. And if you have a friend, if your friend is now standing with you, you could have your friend stand here and hold one end, and you could go to the other end, and then you could walk. And by walking, you're on the end of this other 15 meter long string. By walking around like this, you've now covered all the distances where the next clue could be hiding that are 15 meters away, assuming, of course, that there's no changes in elevation, right? You could have a really sadistic one that says it's 15 meters distance away from here, but it turns out that it's 12 meters along this way, and then sticking on a tree branch that's so many meters above the ground so that it's a straight line 15 meters. All right, so one clue tells you that. That's your scalar version of your clue. The other clue says, actually, this clue, pull out your compass, this clue is 15 meters away, north by east. Maybe it says 30 degrees east of north. Okay, well, if that's the case, now you can sort of draw for yourself a little grid, and you have a north here and you have an east here, and at 30 degrees north of east, that means that this right here is 30 degrees. And so you can see that in this case, instead of just being given a magnitude, I've now been told a magnitude. I'm still going 15 meters, but I've also now been given a direction. This whole compass thing is a direction. Maybe I won't circle it because I've already got my blue 15 meter circle. But I have a direction, okay? So how might I write the vector? Scalar is pretty straightforward to write out. I kind of wrote this here. I said distance is 15 meters. I might also just write d equals 15 meters, 15 m. Okay, but for the vector, how could I have written that? Vector. Well, there are a few ways of specifying vectors. Let's say that you want to be in a flat field and there's no trees, there's no changes in height, you just are looking in directions from where you are. So there are 2 dimensions in this case. Well, you have basically 2 choices. First choice is in Cartesian. So you could specify in Cartesian. The second choice is in polar. And polar kind of has 2 versions as well, which I'll get to in a second. The Cartesian way, and maybe there's a third choice, but it's kind of related to these, which is to use unit vectors. But we're largely not going to do that in algebra-based physics. They're not terribly hard, but they also, for whatever reason, don't usually get introduced at this level. Okay, Cartesian coordinates are kind of akin to saying something like travel, let's say 10 meters along X, then let's say 8 meters along, or let's actually make it bigger. Let's make it 11 meters along Y. Okay, this could also be something like travel 10 meters east, then 11 meters north. Okay, so if you're doing this in terms of a map, probably you're giving east-west and north-south. If you're doing this in terms of just like a coordinate grid, then X and Y is sufficient. And the shorthand way of writing this is you would do a D with a little arrow above it to represent that this is a vector and it's a magnitude and a direction. And we would represent this as 10 meters, comma, 11 meters. Or you could also represent it as 10, comma, 11, and then put the meters on the outside since they have the same common unit. Okay, so this is kind of like Cartesian form of doing this. All right, the polar form is more akin to the direction that I said earlier, that would say like travel 15 meters in a direction of 60 degrees, east, north of east. I'm writing it backwards. Or travel 15 meters, again, in a direction of 30 degrees east of north. Usually when you're doing by map, you might do like east or west of north or south, but either one works. Sometimes you just go with the smallest angle. In a standard grid, it's usually travel 15 meters at 60 degrees counterclockwise from positive X would be the equivalent of this statement. And the way that I might represent that I usually use curly brackets, others don't, but I usually use a curly bracket as opposed to a parenthesis. And you would write that as like 15 meters, comma, 60 degrees. So that would be this one. Or 15 meters, comma, and this one, this east of north, this would be north 30 degrees east, for what it's worth. Okay. Now the unit vectors version is actually quite useful, but you kind of have to understand what the unit vectors are doing. Let's just write this one in terms of unit vectors. So D, and it turns out that with unit vector form, we don't have to put this represented by sign. The little dot over an equal sign again means represented by. When you're using unit vectors, you actually can just say equals, and it'd basically be 10 I hat plus 11 j hat, parenthetically meters. Or you could also write this as 10x hat plus 11 y hat meters. Or if you're doing the east and north thing, this one might be something like 10 east plus 11 north meters. Okay, so basically the I hat means whatever distance you've been given, turn to face in east or x or whatever you've defined to be your x direction, or x hat, same thing. Turn to face that direction and then walk this many meters. And then when you get to the end of those 10 meters, turn to face the new direction, say north or y, and walk another 11 meters. Okay, what about in 3D? I've noted this for kind of completeness, but a lot of what I will end up doing kind of follows either this notation or this notation, just for consistency's sake. But this right here is sort of the preferred notation for it. What about in 3 dimensions? Well, Cartesian looks basically the same. We just get one more term. So travel 10 meters in, let's say, east, 11 meters north, and let's say like look up 2 meters. This could then be represented as 10, 11, 2. And it's always x, y, z, or east, west, north, south, up, down. It's always the ordering of it for these. Okay, and by the way, what if this one was travel 10 meters east and 11 meters south instead of north, and look down by 1 meter or something like that? Well, this one would now be represented by essentially 10 -11, -1. Okay? So that's your Cartesian version. Polar now gets two versions. It now has cylindrical and it has spherical. In cylindrical notation, we'd have like r, comma, theta, comma, z. In spherical, r, comma, theta, comma, phi. And for what it's worth, going back to 2D, Cartesian, it's x, comma, y. Polar, it would be r, comma, theta. All right, so x, comma, y is 10 meters, comma, 11 meters for x and for y. R, comma, theta is 15 meters, comma, 60 degrees for r and theta. All right, so coming here, this r and this theta are the same as this r and this theta, and now we just have an extra z term, which is look up or down. So this is basically how far to walk, what direction to walk in, and this one right here would be look up or down. Okay, and then spherical, this is more like if instead of walking, if you were able to just float or fly somehow. So you just are going to go in an exact straight line, including upward, including forward, including left, right. So this is straight line distance. This one right here is, and this one right here is giving us direction. So this is essentially direction as defined here. This is essentially kind of like inverse of elevation. So what angle of, we'll call it elevation, but it's probably more correct to say like declension. 0 degrees usually actually means straight upward. And so if you are not elevating at all, you're actually more like 90 degrees. Okay. So that basically is our vectors. And you may be wondering, how do you convert from one to the next? Okay. And for a college physics course, like an algebra-based physics course, not the calculus-based, we're primarily going to be focusing in 2 dimensions. So the primary ones are this and this. And so that's what I want to use for conversion. Okay. So if I want to convert from one to the other, how might I do that? So this is kind of the last little thing, converting from, let's say from polar to Cartesian, and then we'll also do one that is converting from Cartesian back to polar. Okay, so this one could be from Cartesian to polar. Okay, so again, this is converting from r comma theta to x comma y. And the basic procedure is this. Let's say that you are told generically an r, and a theta. So I'm going to draw for myself an xy axis here. Y will be my vertical, and x will be my horizontal. Now let's say that you've been given a vector that ends up here. Okay, so this has a length of r, this has an angle of theta to it. In xy form, generic angle with no further specification is assumed counterclockwise from the positive x-axis. Unless specified otherwise, that's the angle that you should draw. So this angle is somewhere between 90 and 180 in this case. So if I want to get from r theta to xy, it turns out that I can do that just using the simple unit circle. So x will be r times cosine theta, y will be r times sine of theta. That's it. That's all we need. Now if I want to get from Cartesian to polar, a similar thing should work. I should be able to basically do the same thing in reverse, but there's a little bit of a caveat based on your calculator. So again, let's say that this is my origin. Let's say that this is my x-axis and this is my y-axis. And let's say that I have been told go, to the left or whatever, negative x some distance, and then go some distance in the y direction. And so my resulting in polar would be this r and this theta. So here's x, here's y. Well, the general rule is that r squared is x squared plus y squared, and that will work regardless of your calculator. And likewise, the general rule is that tangent of theta should be equal to y over x, and that's the one that you have to be kind of careful with. Okay, so these two should be correct regardless. The problem is that most people's calculators are programmed in such a way that they give answers between usually plus and minus 90 degrees, or plus pi over 2 and minus pi over 2. And so it turns out that there is what we would call a twofold degeneracy, because when your calculator calculates things, if you want to get theta from this, you'd say theta therefore is the inverse tangent of y over x. But depending on how your calculator is programmed and how you enter these numbers, you may say like y over x and then hit enter, and it'll say, oh, this is a negative number because y is positive and x is negative here. And it turns out that there's two ways of getting a negative number for y over x. One of them is to have this right here, and the other is to have the exact same sort of ratios of y and x, but in this quadrant instead. So you end up with the same amount of y and the same amount of x, but now x is positive and y is negative. So your calculator doesn't really have a way of distinguishing between these two values, and since it prefers, for most people, an angle between 90 and minus 90, it's actually going to find you this angle. Now, never fear, because this angle right here and this angle right here are congruent, and so if you subtract this angle from 180, then you have the correct angle for theta. But you kind of have to pay attention to whether y was positive or negative, whether x was positive or negative. The same thing is true, by the way, if you're looking at first and third quadrants. So if you do negative value for y, negative value for x, that means you're down here somewhere, but if you do that and then hit enter, you get a positive value, and so your calculator will tell you an angle that's over here. And so you have to pay attention to where x and y are actually located. Now, one way of going about this, sort of like getting a shortcut around this, is this. Let's make one last slide here. And so again, let's say that we're given a generic x and y, and it puts us in some arbitrary quadrant. Okay. So let us say that we're told a value for x, we're told a value for y. So here's y, here's x. This is your x-axis, this is your y-axis. We want to know what is this thing right here, and we want to do it with actual certainty. Well, what you can always do is, your r value you're going to get correct, because you're squaring this, then you're adding them, then you're taking a square root. It's Pythagorean theorem. You can always go and say, I want to figure out what this angle right here is, and this angle, tangent of phi, the interior angle of this triangle, is always going to be the absolute value of y over x. Okay? So in other words, treat y and x like they're both positive numbers. This will get you the correct value for phi. So phi will be the inverse tangent of whatever positive y over positive x is, or absolute value of y over absolute value of x. But to get theta, you then have to do a little bit more geometry. So if you happen to have this as your phi, you can see that phi and theta add to 180. Okay? Different scenario. What if you end up, say, in this axis down here? All right, so you've been told a value for x and a value for y. All right, so here's your y, here's your x. They both end up being negative. Again, this right here would be the correct value for theta if you're trying to always specify as counterclockwise from positive x. This right here would be your value for phi. Notice that in this case, again, tangent phi is y over x, and you can take an absolute value of the y over x, but since they're both negative, they'll give you a positive answer anyway. Again, we can say that tangent inverse of y over x is giving us our value for phi. But whereas up here we said theta is 180 degrees minus phi, down here we would say that theta is actually 180 degrees plus phi. Okay, and so basically you just figure out what quadrant you're in, draw a triangle, choose phi in such a way that y is opposite of it and x is adjacent to it, find the tangent, and then ask, how do I get from that phi to theta? Am I adding it to 180? Am I subtracting 180? Am I adding 270? Am I subtracting 360? Do I have to add or subtract anything, or what? Now this video has already been fairly long, but I think you all who are watching deserve some sort of example for this conversion from Cartesian to polar. Okay, so here's an example. Let's say that you're told that you're going to be traveling 200 meters due west. That would be like the negative x direction, just for reference, on an xy Cartesian coordinate system. So you're traveling 200 meters due west and then 150 meters due north, which for what it's worth would be like the positive y direction on a Cartesian coordinates. And so we want to know what this is in terms of each of these coordinate systems, and just for fun maybe also unit vectors Cartesian. One tip for physics in general, it's helpful to draw for yourself a good diagram. So I'm going to draw for myself a diagram. I'm going to label my x direction and also east. I'm going to label for myself the y direction, which is north. This, of course, is negative y, which is south. This over here would be negative x, which is west. Okay, I'm told to go 200 meters due west, so that would be like 200 this way, and then 150 due north, so that would be like 150 this way. So this is 150, this is 200, both in meters. That means that my actual sort of straight line path would be like this. Okay, and so I have angle theta here. That means that I have an angle phi here, and I will call this angle, for what it's worth, like call it theta c for compass. Okay, and then the distance here would be r. So I've drawn like a diagram that mostly wastes space. I can always sort of redraw it if I'd like, that is a little more space efficient, which would be more like this. And again, I'm going in this direction first, then I'm going in this direction for some distance, and this right here would then be my sort of like straight line, to the best I can draw a straight line with my setup, part of my triangle. So here's r. X and y are always a right angle to each other, so this is always going to be a right triangle. This angle is phi, this angle is theta, and then this angle is my compass angle. Or I could maybe use this angle depending on how I want to write things. So in terms of Cartesian coordinates, my where I have gone, this would we might call it displacement for what it's worth, would be negative 200 meters, because I went to the negative x direction, comma, and you can include or not include the positive, because without it, it's just assume positive. So, comma, positive 150 meters. Okay, for what it's worth, in unit vectors Cartesian, this would be the same thing as negative 200 x direction plus 150 y direction meters, or by convention, negative 200 I hat direction plus 150 j hat direction. Okay, so now we get to the meat of the problem, which is getting this into polar and maybe compass coordinate directions. So polar coordinates. First of all, r squared should look like x squared plus y squared. That means that r is given by the square root of x squared plus y squared. And so that means that r should look like square root of negative 200 meters squared. Squaring that gets rid of that negative sign. And plus 150 meters squared. And basically you just go to your calculator. 200 squared should be 40,000. The other one should be 22,500. So looks like we're taking the square root, if you add those together, of 62,500. And what you end up with is 250 for what it's worth. So this is 250 meters. Okay, this is my interior angle. This is 150. This down here, for the purpose of finding this, is 200. So tangent of phi is 150 over 200, which is 0.75. So make sure you're in degree mode on your calculator and do the tan negative 1 of 0.75. And that gets us 36.86. So let's call it 37 degrees. So phi is tan -1 of 0.75 is about 37 degrees. Okay, that means that theta must be 180 degrees minus 37 degrees. Okay, and so that comes out to 143 degrees. So in polar coordinates, D in polar coordinates would be represented by 250 meters, comma, 143 degrees. Okay, now what about, and I'll just switch colors here because I'm running out of space. What about map coordinates or compass coordinates? So this right here is the answer to B. The answer to C, compass coordinates. Well, for compass coordinates, we use the exact same magnitude as we got for polar coordinates, so 250 meters. And the direction would be, if we wanted to do west of north, it'd be this angle right here. So that's 90 minus 37, which is 53 degrees for what it's worth. And so we could write this as north 53 degrees west. This is 53 degrees west of north. You could also reverse these two and just use the 37 degrees that we found for phi. But usually it's north angle west, or north angle east, or south angle west, south angle east. All right, well, this video is a lot longer than I wanted to make for a short video, but it covers about everything I wanted to introduce you to for vectors and scalars. Now, beware, there will be some more in this class, and you may also want to review the video on right triangles if you got a little lost on these conversions. Okay, so that's it for today. I hope that this is helpful to you, and I hope you learned something, and I'll see you in the next video.